Have you ever wondered what makes up everything around us? From the air we breathe to the stars in the night sky, everything is composed of tiny particles called atoms. Electrons are fundamental particles that carry a negative electric charge. They are incredibly small, about 1,800 times lighter than the smallest atom, hydrogen. Despite their size, electrons play a crucial role in the structure and behavior of matter. They are responsible for chemical bonding, electrical conductivity, and many other phenomena that shape our world. In this journey through time, we'll delve into the fascinating story of how the electron was discovered, explore its unique properties, and uncover its profound impact on our world. Imagine a time when electricity was still a mysterious force, and the atom was thought to be the smallest indivisible unit of matter. The late 19th century was a time of great scientific exploration, with researchers around the world striving to unlock the secrets of the universe. At that time, scientists were particularly intrigued by a phenomenon known as cathode rays. These rays were observed in vacuum tubes, which were glass tubes with most of the air removed. When a high voltage was applied across two electrodes inside the tube, a mysterious glow emanated from the negative electrode, known as the cathode. These cathode rays seemed to travel in straight lines and could cast shadows, suggesting they were composed of some kind of particles. However, their nature remained a mystery. It was in this era of scientific curiosity and discovery that a brilliant physicist named J.J. Thomson stepped onto the stage, forever changing our understanding of the atom. Cathode rays, first observed in the mid-19th century, captivated scientists worldwide. These beams from the negative electrode in glass tubes had properties that defied explanation. They traveled in straight lines, cast shadows, and caused materials to fluoresce, hinting at something fundamental. The nature of these rays sparked debate. Some thought they were waves, others streams of particles. Each had compelling arguments, but proof was elusive. Experiments peeled back layers of mystery. They were deflected by magnetic fields like charged particles. Mass measurements were perplexing, suggesting they were incredibly light, lighter than atoms. J.J. Thomson, a physicist at Cambridge, challenged scientific dogma to unravel the nature of cathode rays. In 1897, at the Cavendish Laboratory in Cambridge, England, J.J. Thomson conducted a series of groundbreaking experiments that would forever change our understanding of the atom. Intrigued by the enigmatic nature of cathode rays, Thomson set out to determine their true nature once and for all. Thomson's experimental setup was deceptively simple yet ingenious. He utilized a cathode ray tube with a modified design, incorporating electric and magnetic fields perpendicular to the path of the rays. By carefully adjusting the strength of these fields, he could deflect the rays and study their behavior. Through meticulous observation and analysis, Thomson made a series of crucial discoveries. First, he confirmed that cathode rays were indeed deflected by both electric and magnetic fields, confirming their charged nature. Moreover, the direction of deflection indicated that these rays carried a negative charge. To his astonishment, Thomson's calculations revealed that the charge-to-mass ratio of cathode ray particles was significantly larger than that of any known atom or ion. This finding implied that these particles were either incredibly light or carried an enormous charge. Thomson's groundbreaking experiments with cathode rays sent shockwaves through the scientific community. The implications of his findings were profound. The atom, once thought to be the smallest indivisible unit of matter, was not so indivisible after all. There existed even smaller particles, constituents of the atom itself. Thomson boldly proposed that cathode rays were composed of these tiny, negatively charged particles, which he named corpuscles. This model, later dubbed the plum pudding model, became the prevailing atomic model of the time. Thomson's corpuscles, later renamed electrons by other scientists, were the first subatomic particles ever discovered. Their discovery shattered the prevailing notion of the atom as a fundamental, indivisible entity and ushered in a new era of atomic physics. Thomson's discovery of the electron necessitated a new model of the atom, one that incorporated these negatively charged particles. The prevailing model at the time, proposed by John Dalton, envisioned atoms as tiny, indivisible spheres. However, the existence of electrons, smaller constituents of the atom, rendered Dalton's model obsolete. To accommodate his newfound electrons, Thomson proposed the plum pudding model of the atom. This model depicted the atom as a positively charged sphere, with negatively charged electrons embedded within it like plums scattered throughout a pudding. While the plum pudding model represented a significant advancement over Dalton's indivisible sphere, it was not without its limitations. It could not, for instance, explain the line spectra observed when elements were heated, nor could it account for the atom's stability if electrons were constantly emitting radiation as they orbited within the positive sphere. Despite its shortcomings, the plum pudding model served as a crucial stepping stone towards a more accurate and comprehensive understanding of the atom. As scientists delved deeper into the atom, they encountered the strange laws of quantum mechanics. In this realm, particles could behave like waves, and waves could exhibit particle-like properties. The electron was no exception. Early 20th century experiments revealed that electrons, discovered by J.J. Thomson, could also exhibit wave-like behavior. This wave-particle duality shattered the classical view of particles and waves as distinct entities, demonstrated through the double-slit experiment, where electrons exhibited an interference pattern, a hallmark of wave behavior. This phenomenon could only be explained if electrons also possessed wave-like characteristics. This revelation had profound implications for our understanding of the universe. The concept of wave-particle duality is one of the most mind-bending ideas in quantum mechanics, challenging our everyday intuition about the nature of reality. It states that particles, like electrons, can exhibit both particle-like and wave-like behavior depending on the experimental setup used to observe them. Imagine a stream of electrons passing through two closely spaced slits. If electrons were purely particles, we would expect to see two distinct bands on a screen behind the slits, corresponding to the two possible paths the electrons could take. However, when this experiment is actually performed, we observe something astonishing. An interference pattern, characterized by alternating bright and dark bands, emerges on the screen. This pattern is a hallmark of wave behavior, indicating that the electrons are interfering with each other like waves in a pond. The answer lies in the heart of quantum mechanics, which tells us that particles do not have definite positions or trajectories, but rather exist as probability waves. The discovery of the electron and the subsequent unraveling of its properties have had a profound impact on technology, shaping the modern world in countless ways. From the ubiquitous electronics that permeate our lives to the advanced medical imaging techniques that diagnose and treat diseases, the electron's influence is all-pervading. One of the most significant technological applications of electrons lies in the field of electronics. Electronics relies on the controlled flow of electrons through materials like semiconductors to process and transmit information. This flow of electrons forms the basis of computers, smartphones, televisions, and countless other electronic devices that have become indispensable to modern life. Electrons also play a crucial role in power generation and distribution. Power plants generate electricity by harnessing the movement of electrons, typically through electromagnetic induction. This electricity is then transmitted through a vast network of power lines, delivering power to homes and businesses around the world. In the realm of medicine, electrons are utilized in various imaging techniques that allow doctors to peer inside the human body without invasive procedures. Beyond its technological applications, the electron has proven to be an invaluable tool for scientists seeking to unravel the mysteries of the universe. By studying the behavior of electrons in various environments, from the depths of atoms to the vast expanse of space, researchers have gained profound insights into the fundamental laws governing the cosmos. Astrophysicists, for instance, rely on the detection of electromagnetic radiation, including light, radio waves, and X-rays, to study celestial objects. This radiation is often produced by the acceleration of charged particles, including electrons, providing clues about the composition, temperature, and magnetic fields of distant stars and galaxies. Particle physicists, on the other hand, probe the fundamental constituents of matter and the forces that govern their interactions. The electron, once a mysterious entity observed in cathode ray tubes, has become an indispensable tool for scientific exploration, illuminating the universe's deepest secrets and pushing the boundaries of human knowledge. As we delve deeper into the 21st century, the future of electron research promises to be transformative. scientists explore the electron's unique properties, aiming to harness its potential for technological advancements. One area is developing new materials with tailored electronic properties. By manipulating electron behavior, scientists aim to create superconductors with zero resistance, more efficient solar cells, and novel electronic devices. Quantum computing is another promising field. Quantum computers exploit quantum mechanics principles, including superposition and entanglement, to perform calculations at unprecedented speeds. They could revolutionize fields like medicine and AI. The electron promises to play a prominent role in shaping the future of science and technology.